everybody give me their tally for player one's winnings.
10.
You got 10? Okay. And that means player two got 10. Wow, 50-50. Who knew? So what percent? Oh, this is tough math right here.
500.
No, it's a 50%. Don't judge. Fine. No, it is 50%. Wow, y'all are so judgy. Lord. All right, so how many times did they win? Well, this is easy. Write as a proportion, 10 out of 20. Now your numbers will look different, right? Because every sample is different. Sampling variability. Now, okay, so who won more often? How many of you guys had player, like theirs doesn't count because it's tied, but the rest of your groups, how many of you had player one win? 1, 2, 3, 4. 4 groups, okay, out of 6. So I guess player two. So your theory, your hypothesis is maybe player one does have an advantage, right? So I play the game. I mean, my friends play the game 320 times. Not really. But in those 320 times, player one won 138 times. So what proportion is that? So 138 out of 320. What's a proportion? It's just a decimal or a percent, right? Yes, of course, you can use your calculators. But I'll do it for you real quick, like 4.431. So then how would I find the proportion of player wins for player two? 1 minus 0.431. Does that make sense to everybody? Why is that the way it works? 0.569 is what it is. Why does it work that way? You know this logically. I'm supposed to see if you put words on it. They have to add up to 100%, right? And there's only 2 options, right? Yeah. So logically, they have to add up to 1. All right, so to determine the true probability of a player one winning, we would list out all the possible roles that we could get. All right, so complete the table to show all the possible roles. So this is like old multiplication tables really quick. So we have 1, 1, then we go 1, 2, 1, 3, 1, 4. I'll give you a second to do it with me. And then we go 2, 1, 2, 2. So if the largest value is at 1, 2, 3, or 4, so I'm going to highlight the largest values being 1, 2, 3, or 1 is the highest? Yeah. Say 1. Highest values are 4. Oops, that's all right. All right, so what you got? So player 2 wins when it's green, player 1 wins when it's yellow. So let's look at probabilities. So how many different, this is what we call, by the way, a sample space. Oopsies. When you've listed out all the possible combinations, a sample space, or outcomes, all right? So we have 6 by 6, so there's 36 total, right? Okay, how many of those did player 1 win? 16? Yeah, 4 by 4. 16, which reduces by 4, would give me 4/9, which is, what, 0.44? All right. So which was closer to the probability that we found in 4A? Not in 4A. Your group's data or the Dobbs data? Like here's what we found when I had a sample of 320. But your group for player 1, what did you have? Which one is closer to the 0.44? That one, the big group or your smaller group? The bigger group, right? Everybody agree with that? Bigger group, okay, the bigger group. Why do you think that is? Oopsies. Huh? I can't hear you. More data? Yep. More data. Bigger samples make a bigger difference, right? So this is what we call, and we're going to talk about this, this is what you call the law of large numbers. Okay? Law of large numbers. Probability isn't determined by a small sample of 20 or 10, right? If it was, then we would think the probability of winning this dice game is 50-50. But we know it's not, right? We need to do it many, many, many times to really get an idea of what's the true probability of winning. If we couldn't calculate it ourselves, we'd have to do it many times. So that's why this is called the theoretical probability when you calculate it from the sample space. And what we calculated here based on an experiment is called the empirical probability. Okay? So those become almost identical the bigger our sample becomes. All right? So your empirical evidence may not match the theoretical, but that's probably because your sample's small. Make okay sense? All right, great. So, turning the page. So, probability model. So when you see this, a probability model, listing all the possible outcomes is called the sample space. And we list their probabilities. And their probabilities. So I'll show you one here in a second. Now, how do you know if it's a valid model? Does it really work? Well, you already told me this. You know they all have to add up to 1 because 100% is the highest a probability can be. And all the outcomes have to add up to that. And each probability is between 0 and 1, usually meaning it's a decimal. It's a decimal value, okay? Which logically you're like, yes, of course it does, right? You can't have a probability of 150%. It doesn't work like that. Now there's some basic rules here. Some of these you know, some of these you don't. Now this one you already did. You may not know the name. The complement of a probability. It's the probability of the event not happening. So you said, you know, we took the probability of player 1 winning and we subtracted it from 1 and we got the probability of player 2, right? So if player 1 is capital A, the probability of not player 1, that we say the little c, we read it as not player 1, which we know is player 2, is just 1 minus the probability of A. All right? Then we have some terminology which you've heard. You just got to stop and think, okay? Mutually exclusive. Mutually exclusive events cannot occur together. For instance, it cannot be Thursday and Friday at the same time. It can't, right? We know that. It's one or the other. They completely cannot overlap. And then the last idea here is the general addition rule. Or, okay, so this comes into play anytime you see a question about does this or this happen. If the two are mutually exclusive, meaning there's no overlap, then all you have to do is add them. Probability of A plus the probability of B. Okay, as long as there's no overlap. And in probability, we use some symbols that are kind of weird, but we would say probability of A or B. It looks like a U, but we read it as or, if it's mutually exclusive. So then the question becomes, okay, what if there's overlap, right? That's going to come on a different day, but here it is for you. If there are overlapping events, then here's how we do it. Probability of A or B is the probability of A plus the probability of B, and then we subtract the overlap, the probability of A and B. So that's what we'll find as the overlap in a table or something. I'll show you how to do it, okay? But just so you have it, it's there. All right, let's try one of these. Pew Research reported that among mothers, family size is shrinking. Suppose we are to randomly select one mother aged 40 to 44 and record the number of children that she has. Here's the probability model. So we've got to decide, is it valid? Two things that have to happen or check for. Do all the probabilities add up to 1? So we put them in our calculator and we add them up. 0.22 plus 0.41 plus 24 plus 13. And they do. So this is how you show your work on that. You just put them together and show me that they add up to 1. That's the first criteria that has to be checked, all right? The second criteria, we mentioned it right here, all the probabilities have to be between 0 and 1. So look at the probability values. Are they less than 1? Yes, but they're greater than 0, right? So then I would just state that. I would say all probabilities 0 and 1. So the two criteria have been checked. That's what makes it valid. It's a very, very common question here, okay? All right, so look at B. Explain why the events have one child and have two children are mutually exclusive. You can have two children and only have one, right? It's just not possible, right? So you know this, it's just putting words together. Okay, so you can't have exactly one child and exactly two children at the same time. Alrighty? All right then, for each of the following, write the event using proper notation and find the probability from the table above. All right, so we're going to practice notation a little bit so you get comfortable. Find the probability a randomly selected mother has less than two children. So less than is an inequality. I'll remember this. So if I put symbols as probability that the number of children, what do we want to say, C, is less than 2? How would we find that? What values in my table are less than 2? 1. It only has one answer, so it's just 0.22, right? That's it. Can handle so far, right? Probability that a randomly selected has 1 or 2 children. We already said they're mutually exclusive, so there's no chance of it overlapping. So what would we do? We say probability that it's 1 or 2 children. So it'd be 0.22 plus 0.41, which gives me 0.63. And then find the probability the randomly selected mother does not have 4 or more children. Does not have 4 or more children. So what would I do there?
1 minus 1.
2 ways to do it. Yes, you can do 1 minus 0.13, right? So if she does not have 4 or more, that means she has less than or equal to 3, right? 0.87. Now, another way you could have done this is you could have just added probability of 1 plus 2 plus 3. And you would end up at the same place. You would still get 0.87. Either method's fine. Okay? With a small set like this, then neither one is hard, but when you have a large set, sometimes it's easier just to do the complement thing. Are we good? Easy enough, right?